The end Permian extinction, also known as a PT extinction or Great Dying, was the single most catastrophic extinction event to ever occur on Earth. This event happened about 253 million years ago, with the main cause speculated to be from a large-scale volcanism event. The extinction itself lasted 200,000 years or less. This event marked the end of the Paleozoic era and the beginning of the Mesozoic era. During the Great Dying, 95% of marine animals were wiped out, as well as 70% of land organisms were killed. This event is the closest the Earth has come to being devoid of all life, and is the biggest mass extinction that has occurred out of the past 5 mass extinctions. The beginning of the Paleozoic era began with the Cambrian period, where life flourished. Biologists are not sure if this is due to high oxygen levels or other factors, such as the evolutionary trait of vision coming into play for the first time. Ancient seabeds from this time indicate rocks were very soluble. With the more soluble a rock is, the more oxygen is present. The most abundant era of life was unfortunately followed by the worst mass extinction known to Earth. We are not sure what the main cause of the Great Dying was, but there are a lot of potential theories such as the Siberian traps and volcanism, Pangea supercontinent breakup, meteor impact buried by new seafloor, or anoxia. It is likely that the Permian Triassic event was a mixture of several factors playing into the other, a positive loop that kept getting worse. For today, we will focus on the Siberian traps as one of the larger causes of this extinction event, as well as their impact on the ocean and the atmosphere. Siberian traps. When we think of eruptions spewing lava, we probably think of Mount St. Helens, Krakatoa, or even Yellowstone. However, flood basalts are terrifying in comparison to our previous examples. The Siberian traps fall under this category. Scientists suspect that massive volcanic activity in the Siberian traps may have had a role in the global die-off, raising air and sea temperatures and releasing toxic amounts of greenhouse gases into the atmosphere over a very short period of time. The Siberian traps are a large mass of volcanic rock located in modern-day Siberia, Russia. Around 250 million years ago, these would have been located in northern Pangea. They were formed from a large volcanic event that began 300,000 years before the official beginning of the Great Dying. Enough lava was spewed out to cover an area the size of Greenland. When flood basalts occur, these are categorized as large igneous provinces, also known as LIP. The original span of lava flow must have been 4 million kilometers squared. The cause of the Siberian traps? Most likely a mantle plume. Mantle plumes form in the lithosphere and rise upward due to convection, where partial melting allows magma to reach the Earth's surface. Think of them as bubbles of extremely hot material rising up inside the Earth towards the crust. These are theorized to be formed from rifting of continents, so in our case, Pangea was going through continental breakup, which may have triggered the large mantle plume. Furthermore, there is evidence in the Siberian traps, large igneous province, which contains volcanic rock that spans 720,000 cubic miles. The common rock found is basalt, creating slow yet prolonged flows of lava at the time it was erupted out. Dolerite, gabbro, and rhyolites are found in the mix as well, but they are not as abundant as basalt. An eruption of this size that spanned over 2 million years would have no doubt spewed insane amounts of carbon dioxide and methane into the atmosphere and the oceans. However, the mass extinction did not occur until after 300,000 years after eruptions began. This brings us to the contact metamorphism theory. Ongoing eruptions spewed lava out quietly in between rock layers after the layers on top served as a lid that did not allow magma to spew out as it had been doing for several years of volcanism. This lid of hardened volcanic rock forced the magma from the mantle plume to travel elsewhere. This led to sills contacting volatile fertile sediments and releasing large greenhouse gases, including halocarbons, through large explosive eruptions that occurred once the material was able to reach above ground. In comparison to quiet flood basalts, contact metamorphism made explosions were much more violent and destructive. Gases that were only emitted out due to heating of surrounding rock were able to disperse extreme amounts of greenhouse gases into the air, way more than the initial flood basalt eruption had released. Halocarbons destroy the stratospheric ozone, allowing ultraviolet radiation to reach the Earth, and these were a byproduct of contact metamorphism eruptions. Evidence suggests sills and dikes in the traps are at least 350 meters thick, making up slightly more than half of the basin. We can theorize that the first 300,000 years of volcanism from the Siberian traps were quiet lava spewing into the surface. Large amounts of volcanic rock were able to accumulate and pile up. During the same time the official extinction event began, we saw the formation of sills caused by contact metamorphism occur. suddenly spewing out dangerous amounts of gases and lava into the air. We can pinpoint this to be the beginning of the Permian extinction, one that would start a dangerous domino effect on other areas of the planet. Because the release of carbon dioxide by seals made the planet heat up immensely, the previously unaffected oceans took the hardest hit next. Chemistry of the oceans. Oceans went through acidification, oxygen loss, and increased temperature during the Great Dying. Because carbon dioxide being pumped out of the Siberian traps was larger now due to contact metamorphism, the ocean absorbed a large amount of CO2 and in turn became acidic. Excess CO2 in the ocean means more hydrogen absorbed quickly, forming carbonic acid and breaking down into hydrogen ion and bicarbonate. As the ocean acidified, pH decreased and killed off marine life. The ocean reached a high temperature of 104 degrees, and not just through the absorption of carbon dioxide. Furthermore, the eruptions that occurred on top of oceanic areas caused by the same Siberian traps also broke down methane hydrate deposits that were produced over millions of years by tiny organisms, deposits that had been frozen deep in the ocean over time. When the deposits were melted and released, catastrophe ensued and temperatures rose by 10.8 degrees Fahrenheit more, contributing to the highest temperature of the ocean at the time being 104 degrees, as mentioned a few moments ago. There was a loss of oxygen caused by oceanic warming, known as anoxia. The oceans became so anoxic that sulfur-reducing organisms overtook the chemistry of the oceans and caused massive emissions of toxic hydrogen sulfide. Overall, the ocean took the hardest hit, losing about 95% of all marine life in this one extinction event. The combination of contact metamorphism and volcanism over oceanic areas, as well as an abundance of CO2 and also a cut in oxygen, led to a hot, acidic, oxygen-deprived ocean devoid of any life. Atmospheric effect. Basaltic lavas from Siberian traps have a lot of sulfur dioxide in their chemistry. When the sulfur dioxide is released, water vapor and air plus sulfur dioxide react together to make aerosols that block the sun. It is essentially a large looming cloud over the earth blocking out the sunlight. To worsen things up, acidic rain was also likely caused by the combination of hydrogen chloride and hydrogen fluoride. Acidic rain further devastated fauna and flora. Halocarbons released from contact metamorphism, as mentioned earlier, also tore the ozone layer, allowing radiation to enter the Earth. The results of these events meant a hot, dry environment found throughout the Earth, with no protection from radiation or acid rain for the organisms that remained. Harsh conditions and arid deserts swallowed the Earth, resulting in the death of many organisms, with the exception of very few creatures. Recovery of life. By the end of the Permian extinction event, only about 5% of life remained. Here is a chart showing the difference in amount of marine species over Earth's entire lifespan. Over here, we see the sudden drop in marine species, showing just how bad marine animals were hit by the Great Dying. It is theorized that animals on the bottom of the food chain and at the bottom of the oceanic floor suffered extreme losses due to oxygen levels being worse. However, marine animals made a quicker recovery than land mammals did, with nekton, animals that swim freely such as ammonoids and ichthyosaurs, flourishing. This is in part because the low oxygen levels were mainly near the seafloor, giving these nektons an advantage. Even though some species made a quick comeback, it took 15 million years to bring the entire ecosystem back to complete normalcy. On land, the only species that managed to escape extinction were some therapsids, which were mammal-like reptiles, and the archosaurs. Therapsids were likely to dominate the Earth as the Triassic slowly began to show recovery from the Great Dying. It wasn't until 30 million years after the extinction that the first dinosaurs became more abundant and flourished in a new environment. Mammals also evolved during the Triassic period. Recovery of the planet ranged from 2 to 10 million years, highly depending on the area of Earth, as some places recovered more quickly than others. Even after the extreme loss of life that was caused by the Permian Triassic extinction, life found a way, recovered, and continued to evolve. Perhaps dinosaurs and humans would never have existed without this extinction event. The Permian Triassic extinction, or Great Dying, is an amazing geologic event that we can learn a lot. By looking into the Earth's past, we get a glimpse into where we are headed into the future, as once again oceans and atmospheres begin to warm up. However, life will always find a way.